It's a pleasure to have Dr. Dan Liu on with us today. She is a senior scientist in the Computational Science and Engineering Division at Oak Ridge National Lab. She earned her PhD in computational hydrology from Florida State in 2012, joined ORNL as a postdoc in 2013, and then as research staff in 2016. So she's an expert in AI and machine learning. She's working on many different applications to Earth system and hydrological models, so including uncertainty quantification, data assimilation, data analytics, and the development of kind of physics-informed, explainable, and reliable AI frameworks. In 2023, she received a DOE Early Career Award titled Integrating Machine Learning Models into E3SM for understanding coastal compound flooding. And she also led the development of the Oak Ridge Base Foundation Model for Earth System Predictability, or referred to as ORBIT, which uses over 100 billion parameters for weather prediction. And this project was a finalist for the Gordon Bell Prize in Climate Modeling in 2024 and 2025. So we're going to hear about her work on several of these exciting topics today. So go ahead, Dan.
Yeah, thank you, Dan, for a nice introduction. So good morning, everyone. So please first let me show my presentation. So thank you for the opportunity. Although currently I'm not directly part of the ECSM project, I've been collaborating closely with the team for about 10 years. And my work focuses on applying AI machine learning to advance Earth system modeling, including the emulator development, downscaling, hybrid modeling, and model calibration with uncertainty quantification. So in the next about 25 minutes, I will give a brief overview of our work in these areas. And I hope it will spark some ideas for how we can collaborate further to advance the ECSM and improve our predictive understanding of the Earth system. And with the increase in data, advances in computing power, and our improved scientific understanding, Earth system models have evolved from the empirical models to theoretical models to computational models, and are now moving to a data-driven machine learning model and the big data-powered AI foundation models. And in the third paradigm of the computational modeling, we developed physics-based models to simulate a complex Earth system. For example, our E3SM is a coupled system, including multiple components. And for each component, we use the data model integration approach to improve the predictions. Say, first we collect the data and construct a physical model based on our scientific understanding. And these models contain uncertain parameters that must be calibrated against observations to improve the simulation accuracy. And then we use a calibrated model for prediction. If the predictions are accurate and have small uncertainty, we apply it to inform decision making. And if not, we will incorporate more data and refine the model to enhance the predictive capabilities. So as you can see, this process involves inverse modeling to estimate parameters and forward simulation to generate predictions. And the prediction is usually filled with uncertainty from the data quality, model structure, parameter estimation, and even the initial and boundary conditions. So quantifying and addressing these uncertainties is critical to improving the prediction accuracy and also supporting the informed decision making. And however, as we know, UQ is computationally expensive, requiring large ensembles of model simulations. And many of these runs cannot be performed in parallel. And then to address these challenges, we've developed 3 AI machine learning strategies. The first is the surrogate modeling. So where we build a faster surrogate to approximate the expensive numerical model using ensemble simulations. And then by replacing the physical model with this surrogate during the UQ, we can greatly reduce the computational time. So for example, in one study, we combined the neural networks with a dimension reduction technique to build a surrogate for the ERM model. It accurately simulated 30 years of the annual GPP across the US using only a limited number of ERM ensemble runs. And the second strategy is inversion-free prediction. So traditional prediction workflows first estimate the uncertain parameters through the iterative inversion and then use the calibrated model for prediction. So this process is both time and computational intensive. And our approach skips this extensive inversion step by directly laying the relationship between the observations and the predictions, and then generating the predictions with UQ for a given observed data. So these methods combines the offline simulation, which produce large ensembles in parallel, with the online updating that quickly assimilate new data streams for the prediction improvement. We've applied this method to faster predict the carbon flux using the ERM with 47 uncertain parameters. Similarly, a team from the Livermore Lab and the UT Austin recently used this approach to build a tsunami digital twin capable of real-time probabilistic forecast by continuously assimilating the observations into an ocean model. And I heard this their work also nominated for the Golden Bell Prize finalist this year. And the third approach is generative AI. We developed a diffusion model that generates samples for both the forward and inverse UQ by simply just evaluating the neural networks. And this approach is not only computationally efficient, but also saves a lot of storage compared to the traditional sampling-based methods, such as the Markov chain Monte Carlo sampling. We've successfully applied all these three methods, and in the following, I will briefly introduce the generative AI approach. So as we know, one of the main sources of uncertainty in ERM comes from its parameters. And traditional methods like the MCMC are computationally intensive, even using a faster surrogate. A key limitation here is that the entire calibration process must be repeated each time new observations become available because we need to reconstruct a likelihood function. And then to overcome this, we developed a diffusion-based UQ method using a generative AI. Our objective here is to efficiently draw samples from the parameter potential distribution for the uncertainty estimation. So we first formulate a generative model F that learns the mapping between a Gaussian latent variable Z, the observational data Y, and the parameters X conditional on Y. And the neural network is then trained to approximate the generator F. And once trained, this network can rapidly generate the parameter potential samples for a given observation dataset just by evaluating the standard Gaussian inputs. And then for any new observations, the trained generator can produce potential samples without rerunning the optimization, so making this process both computationally and memory efficient because we only need to store the trained network instead of storing the entire ensembles for UQ. So now let's look at an example here. In this study, we estimated 8 ERM parameters using 5 years of the annual average latent heat flux at one American flux site. We conducted 2 case studies. In the synthetic case, we randomly select one simulation sample as a synthetic observation. And in the real data case, we use the actual site measurements. And to evaluate the performance, we compare the potential distributions estimated by our diffusion-based UQ methods against those obtained from the traditional MCMC. And for a fair comparison, we use the same 1,000 ERM samples. In MCMC simulation, we use these samples to first build the emulator and then evaluate the emulator in the MCMC process. It took about 5 hours to generate the potential samples even after the emulation. And in contrast, the entire DBUQ pipeline completed in less than 10 minutes, achieving about 30 times the speed up. And the results indicate that in 2 synthetic cases, our DBUQ accurately estimates parameter potential distributions, and the prediction samples derived from these potential samples also closely match the synthetic observations. And in the real data case, again, DBUQ shows the high accuracy in approximating the parameter potential distributions while using only a fraction of the computational cost of MCMC. And this efficiency becomes even more critical when scaling to the multiple sites for the large-scale site-specific parameter estimation. So as the method doesn't require rerunning the optimization process for the new observation data. And beyond the ELM, these generative AI methods has also been applied to other models for both forward and inverse UQ. And the source code and the demonstration examples are available on our GitHub page here. And then with advances in the remote sensing and the in situ sensing networks, researchers are increasingly using the data-driven machine learning models to simulate the Earth system, addressing the limitations of the traditional numerical models that cannot fully integrate the multi-scale and multi-type data. And these data-driven approaches have demonstrated successful applications, but critical questions remain about their trustworthiness. So, for example, how can we ensure that machine learning solutions generalize across spatial and temporal scales? After all, we are dealing with a heterogeneous and dynamic Earth system, right? And how can we verify that the models are making accurate predictions for the right reasons? And more importantly, how can we guarantee the reliability of the predictions under the changing environmental conditions? And to address these challenges, we are developing a multimodal, explainable, and reliable AI methods. So, for example, in one study, we used the vision transformer model to extract land surface information from the satellite images, and then combine these features with the meteorological time series and the static catchment attributes to improve the stream flow prediction across the US. And this multimodal approach leverages satellite data for a broad spatial coverage, time series for the detailed temporal dynamics, and the catchment attributes to represent the landscape heterogeneity. And then by integrating these complementary data sources through the advanced AI architectures, we can better capture the complex interactions within the land surface system, so enhancing both the prediction accuracy and the generalizability across the space and the time. And we also applied a suite of explainable AI techniques to validate the model decision and ensure the physical consistency. And this includes the post hoc methods such as the sharp and integrated gradients, which analyze the model behavior after training, as well as some inherently interpretable models like the white box long short-term memory networks and attention-based transformers. This approach quantifies the importance of the input variables and also their temporal importance, helping us identify the key drivers for the predictions. So such analysis not only improve our scientific understanding, but can also guide new data collection and even the process-based model development. In addition, we incorporated a wide range of uncertainty quantification methods to assess the model reliability. And this includes the computationally expensive Bayesian neural networks, the assumption involved the Gaussian process and ensemble-based methods, and also the prediction interval approaches. And this analysis quantify the prediction uncertainty from the data quality, model structure, and the parameter reliability. But more importantly, they help detect out-of-sample situations, telling us when the machine learning model may fail by showing the large uncertainty, so enhancing the model robustness under the changing conditions. And together, these three strategies, multimodal learning, explainable AI, and uncertainty quantification, complement each other to enhance the trustworthiness of the AI machine learning models for Earth system predictions. As we know, AI machine learning models are data-driven, and the earlier generations maybe relied on the physical simulations or the observation data, and most applications used a limited labeled dataset for the specific tasks. But Earth system data are largely unlabeled and multimodal, including the images, time series, point estimate, point measurements, and the graph structure data. Then this raises a question: how can we integrate these heterogeneous data sources to advance a wide range of Earth system applications? Then here the foundation model comes into play. A foundation model is a large-scale neural network trained on the extensive, diverse dataset adaptable to a variety of modeling tasks. These models operate in two phases: pre-training and fine-tuning. During pre-training, the model learns the general Earth system representations from the massive heterogeneous datasets in a self-supervised manner, and then can be fine-tuned for a specific task. So as you can see, these capabilities make the AI foundation models particularly suitable for the Earth system modeling, as the Earth system generates a vast and diverse dataset across the multiple types, scales, and even resolutions. And this data cannot be fully integrated by the traditional numerical models due to the mesh limitation or some physical equations, and also cannot be integrated by the task-specific machine learning models. And recent advances in the vision transformer architecture with multimodal embeddings now enable us to integrate these heterogeneous datasets in a unified framework. And more importantly, Earth system modeling has a broad scientific applications and impacts multiple sectors. So there's a need. And so AI foundation model provides a powerful tool to meet these needs and to improve the prediction accuracy, efficiency, and generalization, while also saving the computational cost and the individual's effort. We are now developing a foundation model for the Earth system modeling called the Orbit. Orbit has been applied to weather forecasting, downscaling, and even the ERM acceleration. And in the weather forecasting, Orbit was pre-trained on the CMIP6 simulation data and fine-tuned on the ERA5 reanalysis data. So we considered 91 variables, including temperature, wind speed, and humidity, spanning the surface through the 17 atmospheric layers. And then to handle this massive data, we used a vision transformer architecture with adaptive tokenization and variable aggregation to enable the effective and efficient learning. And to examine how the performance scales with the model size and the data volume, we designed 4 model sizes ranging from the 100 million to 100 billion parameters. This make Orbit the largest AI model for the Earth system modeling. And compared to the state-of-art numerical, machine learning, and AI models, Orbit achieves a competitive performance in forecasting weather 14 days ahead, and the inference time is less than a second on a single GPU, making a real-time weather forecasting on a personal computer feasible. And this year, we extended Orbit's capability from the weather forecasting to downscaling, so essentially shifting from a temporal prediction problem to a super resolution problem for generating the high resolution weather data. And in downscaling, we pre-trained Orbit to achieve a 4 times spatial refinement across the multiple datasets at both the national and the global scales, and then fine-tuned for specific applications. For example, we downscaled the quarter-degree ERA5 reanalysis data to a kilometer-scale precipitation and temperature over the U.S., validated with day-met observations, and to the high-resolution global precipitation, validated with the emerged satellite data. And to ensure the efficient and the scalable training, we optimized the model architecture. For example, we introduced the residual paths to reduce the quadratic computational complexity of the vision transformer and applied variable aggregation and adaptive spatial compression to further minimize both the computational cost and the memory storage. And running on the frontier supercomputer, Orbit achieved 4.1 exaflops of the sustained throughput with 98% strong scaling efficiency across the 8,000 nodes. That's almost 90% of the entire frontier. We've used Orbit to generate the high-resolution global precipitation data and demonstrated high accuracy across all the 58 IPCC AR6 regions and 9 monsoon areas. And the high-resolution weather data is definitely highly valuable for the impact modeling. And Orbit can downscale the multiple simulations simultaneously and efficiently, enabling the rapid generation of the high-resolution global datasets from the fast cost-resolution model simulations. So for example, we can use the coarse resolution E3SM simulations to quickly produce large ensembles and then apply orbit to downscale them to a kilometer scale resolution for evaluating the energy water system reliability. We are also leveraging orbit architecture to accelerate ERM simulation, and this work is led by Dali, Dan, and Peter Donlens and their team. And building on orbit, we developed a faster surrogate model of the ERM to accelerate biogeochemical simulations, achieving a tenfold speed up while maintaining a high predictive accuracy. And the plan here is to extend this approach to accelerate the entire ELM and ultimately to apply the similar strategy to the ocean models and the other ESSM components, and hopefully creating an AI-enhanced modeling framework. So Orbit has achieved some accomplishments. Its weather forecasting application won the Top Supercomputing Achievement Award and was selected as a Golden Bell Prize finalist last year. And its downscaling effort was nominated for a Best Paper Award and was again selected as a Golden Bell finalist this year. And now we aim to leverage our modeling capabilities to maximize their impact. So for example, we can use the E3SM screen model to accurately simulate weather patterns and then apply Orbit's downscaling capability to generate high-resolution weather data, and then integrate this with the accelerated ERM simulated runoff and the remote sensing products to improve the hydrological predictions that can enhance the energy generation and the water management. So let's look at some examples. We developed a multimodal machine learning model that improves the stream flow prediction up to 30 days ahead across the US. And beyond this national scale, we've applied AI methods to advance the water energy system modeling in some key areas. For example, in the Pacific West, where the seasonal water availability is highly variable, and groundwater banking is essential to balance the water supply and water demand. And we use the machine learning models to predict the groundwater dynamics, enhancing the drought resilience. And in the Mid-Atlantic region, where the accurately simulating the compound flooding is critical, we developed physics machine learning hybrid models to predict the flood depth and extent, supporting the natural hazard mitigation. And also in the southeastern US, where the hydropower and energy facilities play a major role, we applied probabilistic machine learning models to forecast a reservoir inflow 14 days ahead with a UQ on over 100 reservoirs managed by the Tennessee Valley Authority, improving the energy system efficiency and reliability. So as you can see, these examples of the large data-powered AI foundation models and the regional digital twin testbed applications essentially illustrate our two-way modeling approach. In a top-down direction, we leverage the global data and the foundation models to develop the high-fidelity predictions and then fine-tune them for the localized energy-related applications, so enhancing the accuracy and the regional relevance. And in the bottom-up directions, we use a testbed-driven scientific understanding to validate the local process and then scale them up to inform the larger-scale models, so extending the impact across the regions and the systems. To summarize, a system modeling is critical, definitely, and the AI machine learning provides powerful tools to advance the numerical models, data-driven models, and the foundation models. So each modeling strategies, of course, has its own strengths and limitations, and we need to better understand both scientific questions and each modeling approach, and then use the data model integration strategy to improve the system predictability. We have made some progress, but definitely there's still a long way to go. And the AI machine learning can also advance the E3SM modeling capabilities in many ways, so such as the emulator development, hybrid modeling, downscaling, and the model calibration with UQ. In this talk, I briefly showed some of our efforts in these areas, and hopefully they can spark some new ideas and discussions here, so we can work together to further improve our ESSM modeling capabilities. So I'd like to stop here and to see some questions. Thank you.